In this video, I will be discussing and actually proving the relationship between the area under a curve and the antiderivative of the function defining said curve. Before we jump into that proof, let's first observe a specific case, a specific example, so that we can kind of get in our heads what exactly we're proving. If I ask you to solve for the integral from 0 to 2 x dx, what I am in essence asking is give me the area under the curve y equals x from 0 to 2. And that area would look something like this. To solve for that area in a non-geometric way, what you might do is first determine the antiderivative of the function over which we're integrating, in this case just x, and we know that the antiderivative is 1/2 x squared plus c, and then we first evaluate our antiderivative at our upper bound 2, which will be 1/2 times 2 squared, which is just 2, and then we subtract off our antiderivative evaluated now at our lower bound, which would be 1/2 0 squared plus c, which would just be 0. And if you notice, I didn't write the plus c's up here. I could have written our plus c's, so 2 plus c, and then minus 0 plus c, but that would have been to the effect of adding 0, because if I add c here, I'm just going to subtract it here. So our full area comes out to just 2. And solving this, we know that the area under our curve y equals x is 2. And that's what this integral solved. What we will be proving is why exactly we can do this, where to get the area under our curve, what we do is we take this antiderivative, because I don't think it's entirely obvious why the antiderivative has anything to do with getting the area under a curve. Now, the notation perhaps alludes to there being some relationship with both of these two operators using the same squiggle, same signature squiggle, but notation is never a proof for anything, so let's jump into proving this relationship. First, what we're going to do is draw some arbitrary function, and we will just be using this to visualize what exactly we're doing. The actual shape of this function does not matter. Point is, this is some function and some graph of some function, and what we want to do is get the area from a to b on this function. To do that, what we will first do is define some function, another function, big F of x. And what this function will do is give the area under the curve y equals f of x from 0 to x. So if I say big F of 3, what I am asking is give me the area from 0 to 3 under the curve y equals f of x. So with that in mind, and remember, we don't have any definition for how exactly we calculate big F of 3. We just know that it will equal the area from 0 to 3 under our function. So to calculate the area we actually want, the area from A to B, what we do is we first get the area from 0 to B. To do that, it would be big F of B. This will give us all this stuff. And then we subtract off the excess at the beginning, which is from big F, which would be big F of A, and that's all the area from 0 to A under our graph. This here will give us the total area from A to B, just like we want. Now, as said before, we can't really calculate this right now, because if we don't actually have an algebraic expression for big F of x, we sure can't solve for big F of b minus big F of a, because we don't know what that is. What we can do, though, is bound it somewhat rigorously. And the way we're going to do that is first find its lower bound. So we know that it must be greater than or equal than something. And what do we know it'll be greater than or equal to? Well, first let's define some point between A and B. Let's let it be called L. So L will be some point between A and B. And we're going to define this L such that f of L is the minimum of our graph from A to B. On our graph, looks like it would be right about here. This will be L. And f of L then will be this point on our graph. Noting that this is the lowest point on the graph, what we will now do is construct a rectangle whose base is from A to B and whose height is f of L. So constructing that rectangle might look something like this. And we know the area of this rectangle will always be less than the area under our curve, or perhaps equal to the area of our curve if our curve were a flat line. If our curve was just a straight line, the area of the rectangle would be the same as the area under our curve. So we know the area under our function will always be greater than this rectangle. And what is the area of this rectangle? Well, as said before, the height of our rectangle is little f of L. The base is from A to B, so that total length is just B minus A. So now we have a lower bound, and we're going to define an upper bound. So now let's pick a point H such that it is between A and B, and it is f of H is the maximum of our function between A and B. So that looks like that'd be this point right here on our graph. And now we will construct another rectangle, this time with a height of little f of H. So that rectangle will look something like this, and whose base is still from A to B. And we know that this rectangle's area right here will be greater than or equal to the area under our curve from A to B. So let's write that down here. We know that the area of our rectangle, which will be the base times the height of our rectangle, the height of our rectangle is little f of H, and the base of our rectangle is the length from A to B, which is given by B minus A. So now we have some bounds that we can actually calculate. If this were a function with an actual definition, we could actually calculate these bounds. Now, what we're going to do is work with this to get a nice definition for big F of X. The first step we'll take is we will divide through by B minus A. So that will leave us with F of L being less than or equal to the difference between F of B minus F of A, big F of B and big F of A, all divided by B minus A. And this will be less than or equal to little f of H. From here, what we now do is take a limit. We will take the limit as B approaches A. Now, this is going to do a couple things for us that are all super cool. The first thing is, let's look at the middle part of our expression. The limit as B approaches A of big F of B minus big F of A, all divided by B minus A, this will be the derivative of our big F. Because the definition of the derivative of a function, we know to be the limit as H approaches X of F of H minus F of X, all divided by H minus X. So knowing that, we know that this expression here is big F prime of A. And now another nice thing that's going to happen here is because B is now going to A, we're taking the limit as B approaches A, H now being between A and B, we'll be left with nothing but to be A, because if B goes to A, as it is right now, H will now be between A and A. And the only possibility there is A. So we know that f prime of A is less than or equal to little f of A. And the same thing's going to happen here on our lower bound. L is going to be kind of squished in between A and B up until B is A, and we get L to now be A. So our f prime, big F prime of A, is now greater than or equal to little f of A. And big F prime of A being both greater than or equal to little f of A and less than or equal to little f of A leaves it to only possibly being equal to little f of A. So we know that big F prime of A is equal to little f of A. And we're almost done here. Now, all we must do is take the antiderivative of both sides here, and the antiderivative with respect to A of big F prime of A will just be F prime, or just F of A, because we're taking the antiderivative of a derivative, just giving us back our original function, and then on the right side of our expression, we're just going to leave this in the same form, the antiderivative of little f of A with respect to A. So this really has proved exactly what we want. All we need to do is now apply it. So looking at our original problem, we wanted the area from A to B under the curve f, y equals f of x, and we know from how we defined big F, remember, big F is the function which gives the area from 0 to some value under our curve. So we know the area under F from A to B will be big F of B minus big F of A. And substituting in what we know here, big F of B will come out to the antiderivative of little f of B dB, and then big F of A will evaluate to the antiderivative of little f of A dA. And I'm just swapping out the variables because the actual variable here doesn't matter. This thing up here could be f of x equals the antiderivative of little f of x dx. It could be any variable there. And we know that this will give us our area because of how we defined our big F here. And because we know that this expression here, with how we define big F, will give us the area, and we know that this expression equals this expression, we know that this expression gives us our area. And that, my friends, is how we know that we can calculate the area under a curve by taking first the antiderivative of the function which defines that curve, and then taking the difference of that antiderivative evaluated at the starting and end points. Thank you for watching, and I hope you learned something new.